more than 10 years working on all flavors of databases. That's a primary focus area for him. And today he's going to talk about stream processing with Go, but an interesting thing about him is he's very passionate about fish, right? So he was just telling me that he has 3 aquariums at home and 1 at work. And is also, I guess aquariums didn't cut it, he wanted to get up close. He's also a certified scuba diver. So, well, thank you for being here, and over to you.
Thank you. Yeah, so before I start, I can also take a bet saying that half of the people who know me before didn't recognize me, because some people came to my booth and asked, "Where is Sunil?" Asked me. So this is me. It's exactly the same, right? How could you miss the obvious? Okay, so let's get started. So I'm going to talk about stream processing in Go. We'll be proposing a framework and how the framework should work. So why talk about streams, right? Streams is the new norm. It's a new madness, and the Aerospike is also into this madness. So when you talk about streams, right, think about Internet of Things, where you have continuous stream of data flowing from sensors. It could be your Kafka streams, it could be your Storm pipelines, or real-time fraud detection. So what is real-time fraud detection, right? When you're making a credit card transaction, you don't want to be in a situation where the credit card is stolen, and like somebody spends like some 25,000 rupees on your credit card, and your bank sends a email later saying, "Hey, congratulations, somebody stole 25,000 rupees from your credit card, and we know that it's not you who did the transaction." Right? You don't want that. What you want is, like, while the guy is doing the transaction, you want the fraud detection to happen at that point and say, "No, we cannot allow this transaction." Right? So traditionally, if you look into the past, right, data was at rest. So what it means is you used to collect the data, store the data, retrieve it, and process it later. So with the new set of applications, that's not going to make the cut. So you need to be analyzing the data in the streams itself, right? So to talk about a few characteristics of streams, like based on your business needs, you will have like different forms of streams, right? Depending on your business case, like you will collect different types of data, your ad serving data, your mobile data, your web serving data, all that stuff, okay? And the data may come from many different sources, right? You will have like 10 web servers doing the same thing. The data is the same, but the parallelism is more. So you will have a lot of streams like pumping into your central processing unit, not really CPU as in the machine, but somewhere you do the processing. Or the data may come from many different sources, variety of sources, right? The same data or the data having the same characteristics, what you look for, may come as a string, or it may come as a JSON document, it may come as an Excel, right? And you should be able to deal with all forms of data. So today in my talk, I'm going to concentrate a lot more on this variety of data, and the framework we are proposing is to make it easy to handle this variety of streams. Okay, so let me talk a little bit about the relation between Aerospike and the streaming data. So Aerospike has a feature called aggregation, where you can fire a second index query or a scan and say, "I want to do aggregation on all the data that is coming back from the servers." Okay, so what happens behind the scenes is, like when you have this scan or a second index query, it goes to all the nodes of the Aerospike cluster. You perform the first level of reduction or aggregation on each node, and the data comes back to the client. So the client does the final reduction. Take it with an example, right? You just simply want to see how much your company is spending on the salaries, right? You say, like, "Give me everybody's salary," right? So each node of Aerospike cluster first sums it up on the node and sends each sum from each node to the client. So the client simply has to sum up from all the 10 nodes of the cluster and say, "This is the final sum," right? So I talked about a different type of streams before, in the sense, like when I talked about IoT streams and all, it's an unending stream. It will never end, right? But the streams I'm talking about in Aerospike is a finite stream. It will start at the beginning of the query and finish and terminate at the end of the query, but it nevertheless a stream. So I talked about like streams coming from app servers and all, but what does it look for a programmer, right? You don't care about what is the server, what does it look like, what is the business case. you should map into the code, right? When you look at the code, like you simply have arrays, slices, channels, buffers, files, database queries, result set, whatever it could be. All of these are streams, right? What is a common characteristic between all the streams? You should have a function which tells, give me the next element in the stream, right? So we will build on this basic thing. It needs a little bit more than this, but the basic thing common across all the streams is this simple function. So now, we are always talking about variety, right? So now how to handle incoming streams like having variety of data, right? Go doesn't have generics, which is equivalent to the templates in C++ or Java, where you can say like, this is my filter function, it can take any class, right? So now what do? So you should let multiple varieties of data. So one workaround for this, not good, but let's stick to the thought process. You can simply have a boxed interface. What is boxed interface? Interface with nothing. So suddenly everybody qualifies to be part of this stream, right? But there is a problem to that. You don't have type safety, right? So, but it can be worked around, right? So let's say you write your filter functions, map functions, which can handle strings, integers, JSON data, right? But you're not ready to handle, let's say, an XML, right? We don't like that guy. He's a very old guy. So what do? So all the youngsters are ready to party, and like this XML guy comes in. What do? You put a bouncer to kick him out at the gate itself. So what you can do is like you do Go runtime type checking and can say like, okay, I cannot handle this data, so I will filter it out very early. So later, like the development team can kick in and say like, okay, let's see if we can handle him and enhance it later. But at least it will keep the pipeline going on. So the other extreme, right? You can say like anybody who want to enter the stream has to satisfy all these criteria. And so you make them implement a whole bunch of functions so that he can enter the stream. The problem with it happens when you want to add more type of data, because each type of data will have its own characteristics, right? So the interface you designed is very strict, and now you want to add a new guy who may fall a little bit outside the common characteristics of all these guys. I don't have any political affiliation, but we all want Rahul Gandhi to be the Prime Minister, right? But, but the requirements are so strict, we cannot allow that. Right? So what do? You add a clause saying that, okay, you can be part of a dynasty, right? But the problem is that you're doing disservice to a lot of other guys. So what you do is you change the clause saying, okay, you can have a dynasty with 0 or more number of your ancestors being the PM. Now I also qualify to be PM, so I'm happy. Right? But the problem is you're diluting the standards. So like if you keep on doing for every new guy that comes into the picture, you're moving from your strict interface to the generic interface, right? Why have a requirement in the first place, right? So, okay, let's say we are done trying to find a balance between the extreme end and the strict end. So what do you do next, right? You have to compose. Compose in the sense, when you're doing stream processing, you have stages, right? So what it means is like, you want data to pass through the first stage, it does something, and then you pass it to the next stage, it does something, you pass it to the third stage, and it does something else, right? So composing is nothing but the way you link these stages. So one way you can do is like, I just took one example where you had two streams, one coming from a database and one coming from your file servers, let's say, right? So you want to join these streams and then pass it on to the next filter stage. So one way you can do is you can simply say stream1.join and pass stream2 as a parameter to it. But the problem is now only stream1 is capable of doing this join. So if you want stream2 to be capable of that, you should have stream2 also to implement this join function, right? Now, you're not designing a very flexible interface this way. So a slightly better alternative is to have a join function which can take any type of stream and do some join, right? Slightly better than before, but not so good. So the extra burden it provides is like, okay, you have this join phase, and then you have to create a stream and pump it to the next stage. Still not so bad. So what is the problem we are trying to solve, right? I don't want to code, or I want to write very less code, and I don't want to repeat, and I don't want to do the testing, right? I'm a lazy programmer, but lazy in a good way. I want to do something, but I don't want to do much. So, okay, enough of criticism. So let's try to be constructive. Let's try to set some goals and work towards them. So what are the goals we are trying to set for ourselves is, I want to be able to process data coming from different types of streams. What I care as a programmer or a guy dealing with the data is, I only care about the data. I don't really care about where it is coming from. It may come from a stream, it may come from a queue, it may come from a slice, I don't care. So now if you ask me to say, each of this source has to implement a filter, and you almost replicate the same logic in all of this, it doesn't make sense, right? I'm repeating myself. I don't want to do that. So what I really would like to have is a magic function which takes a stream as an input and two functions, a filter function and a map function. I'm just picking as an example with two stages. One is a filter and a map, but I can have n stages. So I can have 3 filters, 3 maps, 2 reducers, it can be anything. And like, to map to a more real world example, I can have a data flowing, coming, transforming. I want to do my real-time fraud detection at one stage, right? So the other goal I want to achieve is, I don't want, as a framework designer, I don't want to be mercy of my programmer who is using the framework, okay? So what the programmer cares, or the user of the framework cares, is about the data. So he has control of the data, he has control of what functions or what filters he want to use, what mapping function he want to use. I don't want to let him control the flow of my framework, flow of the data, because he doesn't really care, right? So what we want, again, is a magic function which just takes a stream, and a filter function and a map function and a whole bunch of processors, okay? So to sum it up, right, so what would a transducer look like in the implementation is, you have a magic function. What it does is, it has a stream. So for each element that is coming from the stream, pass it to the filter function, or whatever stage it is. And if the result comes from the stage, pass it on to the next stage. And if that stage result gives a result, then give it back to the caller, right? So here it's a simple pseudocode using just 2 stages of process. But the notion should be extendable to multiple stages of processing, right? So now things will get complicated. So the whole idea is actually borrowed from Clojure programming language, but Clojure actually stores the ideas of channels from Go, so we are even, so no complaints there. So now, like, how would a generic transducer look like, right? What is transducer is nothing but, you build this chain and say, like, these are the basic properties of my transducer, and this is what it can do. This is how it will link with other stages, okay? So the signature of the transducer is nothing but it will take a reducer and return back a reducer. So I'll try to simplify this. Okay, before this I should warn you, so I'm from scuba diving. So so scuba diving, like when you do scuba diving, like you will have all the gear saying oxygen cylinders and all. But there is something called free diving where you don't have any oxygen cylinders. You hold your breath and take a very deep dive and come back. And the record for that is 4.5 minutes, the world record for it. So you're going to beat that. Please hold the breath for the next 4 slides, because we're going to go very deep into the framework part. The beauty of it is, like, when you come back, like, you will see a very simple interface, which is the blue sky, okay? So transducer is a function which takes a reducer as an input and returns back a reducer. What it does is the magic behind it, okay? So we'll come back to that a little bit later. So what is the basic properties of a reducer, right? Maybe reducer is a bad word here. Don't think of it as a Hadoop's map reduce, but it's just a processing stage. Think of it as a processor. Don't talk, okay, I should stop calling it reducer. I'll call it a processor, okay? So what is the basic properties of a processor? It should have an init function, because some of the stages may want to initialize a state which it may want to carry. So you need an init function, right? And you need a termination function. At the end of this stage, whatever it aggregated, accumulated, or processed, it want to return that, right? When you are tearing down the entire pipeline. And you need a step function which continuously reads from the stream and accumulates it. So if you see the signature of init and complete are very simple. So step function, what it does is it takes an accumulated value, which is already accumulated, and a new value. So all it does is it takes a new value, does something with the pre-accumulated value, and return back the whole thing back. So what it returns is a result again, and a flush boolean, which tells, which is very Aerospike specific, because I was telling the Aerospike problem, it has a finite lifetime, right? It's not a continuous stream. And there could be scenarios where you may want to abort the stream midway, right? So I talked about the real-time fraud detection. So let's say you detected a fraud, you don't want the transaction to continue. So you should, the pipeline itself should have the capability to stop the processing when it want to. So the idea behind this flush is like an abort. If you detect some problem or you don't want to continue, you will signal to everybody ahead of you or behind your queue saying don't process any further, just abort the whole pipeline. Okay? So few data structures, so let's not be worried about that. So but the more important one is how you link all these stages of processors. So what you do is you have a very generic function, which we call it as a compose function. What you are doing is you are composing a pipeline. That means you are building this whole chain. Think of it, you are building a train, you just bring these compartments and link them together, right? So how do you link? So you have a reducer, which think of it as an engine of the train, and then you have a whole bunch of transducers. You don't know what is that count, right? So it's a variable length array, variable length arguments. So what you do is you start with the nth element, right? So L equal to length. You'll know the length of the reducers that is passed by the caller. So what all this for loop is doing is linking n minus 1 to n, n minus 2 n, n minus 1 to n minus 2 to n minus 1, n minus 3 to n minus 1, and so on all the way up to 0. So you prepared a whole train with the engine and all the bogies behind it. So now what it does, right? So okay, before going into what it actually does, so some more interfaces, I just repeated the interface. So init function is nothing but when one stage says init, it will also say, it will do its own initialization. That part is not covered in this signature. But the most important job it does is it will tell you the next guy also to say init. Okay? So same thing with complete. When he says complete, he will finish what he has to do and say the next guy complete. Okay? So you're building the whole chain. So same thing happens with step function also. So step function is taking a accumulated value and the new value that is coming out of the stream. Again, what it does with the value, it's hidden. But more important thing is, once it applies the stage r.m of value, you process that and then pass it to the next step directly. So you're invoking your next guy saying, okay, this is what I collected, now you process this. Okay? So this is the transducer's signature. So like we said, transducer is a function which takes processor as an input, or reducer as an input, and gives back. So it kind of links. This is the guy saying it is returning you a function with this structure who has a reducer, which is your next reducer, and what I do myself. So M is a mapper. So this is an example implementation of what a stage will look like. Okay? So putting all the pieces together, right? So what does transduction involve, right? What would the framework do? So what this framework doing is you have the initial reducer. Sorry, this is the end one. So you compose with the initial reducer. So you're building the whole chain, and then you're saying init. So everybody inits in the whole chain. So then it takes it from the stream. iStream is your input stream. So you do input stream.next. You keep consuming all the data as long as it comes. You pass it to the step function. So you're passing it to the first step function. The job of that step function is to call it throughout the chain. Okay? And like when you're done with everything, so this is the flush I was talking about. If one piece of the stage says don't proceed further, abort, you're just saying you're breaking out of the loop and say complete, complete, complete. So everybody kind of aborts from that point. So this is the final stream, like from the last stage to your application. So this guy simply returns a reduce.stream, which is going back to the application level. Okay, so yeah, so we are back to the surface. So what does it mean, right? Like, so if you understood the last 4 slides, you will understand what a framework designer goes through. So he takes all the pains so that the end result looks so beautiful and all the complexity is hidden behind. Okay, if you didn't understand also it's fine, because it will look something like your annual review where your boss calls you for review and talks giving information, right? But you're not interested about anything that he says. All you want to hear is what is my increment that year, right? So this is the final result of all the discussion that happens. So this is how your application will look like, right? So the framework, when you're calling the framework, that you're just, sorry. So you're just calling the transduce function and saying that this is going to be my stream. And your stream can be anything, right? So here I'm just showing an inner join between a query result and your file result. It could be your channels, it could be your buffer slices, whatever it can be. So this is your input stream, and then you have a whole bunch of transducers following that. Okay? So you have like a filter function which says, I'm giving an example from a DB world, where you have a you have an AND clause where you want to query and pick some bins from that or columns from that, and then you want to transform that using a map function. So you are saying that I want all the people who has name with Gopher and age more than 5. For all the results that is coming out of it, I want to map these fields. I want to forward it to the next stage. And what the next stage is doing is it is taking the top 5 top 5 elements from a sorted array. Okay, so if you notice, right, one thing I intentionally avoided is to not do this sort as a stage in between, before the top 5. So the problem is you are calling, so if you do that, right, let's say you have a filter function and then a map function and then a sort function, and a top 5 function following the sort. The problem doing that way is you're stalling the pipeline, right? Because you need the entire result to come to have a sorted array to take the top 5, right? But you don't, that's not a good idea because you are stalling the pipeline. You just want the data to flow. So what you are doing is you're having a transducer which will always take the top 5 from the previous sorted list. Okay? So you don't want this list also to grow very big, like it could be 10,000 results, but all you care is about the top 5 from each result. So if you get the next 5, like you'll see if any of them is greater than that. If somebody is greater, you'll just kick out the last guy and keep maintaining the top 5 elements at every stage, or every invocation of that stage. Okay? So yeah, that summarizes it about how it will look for an application. So all the machinery is just for the sake of the framework. This is how the final application will look like. So that's pretty much it. So what are the downsides of it? No compile time safety, but we know how to use bouncers to kick out people whom we don't want. And it's tough to parallelize. So that's the trade-off we are making here. So because everything is under one go routine here, the whole pipeline happens in one go routine, right? So now you don't need to do exactly this way. You can try to find a balance between how much you want to do it in one pipeline and how much you want to hand off to the next stage, right? So if you want to go down to that level, you can do that. So you can work around that problem of not able to parallelize this model, okay? But pros, like we have less lines of code. So basically, all the pros sum up. You can just write less code, less testing, more time on Facebook, Instagram, and Snapchat. So that's pretty much it from my side.
Hello. Thank you for the presentation. So I see many similarities between the stream processing and GStreamer, which is a multimedia framework.
Okay.
I mean, whatever you just mentioned as a problem is solved. Of course, not in Go. But there, see, you mentioned about init and step and complete and fleshing.
Right.
So all those are handled uh, as a messages. I mean, the pipeline in GStreamer, it is called pipeline.
Mhm.
So whenever you want to send a message to any of the intermediate element, you send a message. So basically whenever the playback starts, you send a init, and whenever you finished playing all the things and you don't want any buffer or video frame in the pipeline, you send a flash.
Right.
So there it is solved as a generic message. Have you considered using messages, generic messages, instead of separate functions to do that?
That will again go against our idea of writing generic pipelines, right? Here, the framework should not control what should be the message, right? We give the control to the programmer to say when he can call flush. So in a stage, depending on your logic, you decide when to call flush. What the simply the framework is providing is the ability to say, I want to flush, but not the specific message to flush. Then it becomes like, again, non-generic, right? The problem we are trying to solve is have a framework which can handle anything.
Yeah, I mean, if it is anything, so I could give an example. Let's say you have a chain of stream. I mean, you are just sharing the head of the stream to some other process or function,
Right.
and that function want to send or change some property of second stream. So it has no way to access the second
Oh,
stream.
you can still flow the data. So what we are
No,
saying is,
I'm not talking about data. Some parameter, how it work on the data that I want to
Yeah.
change it on the second stream. How do I access the second stream in the first place, and how do I communicate with that?
so if I understood your question correct, right? You want to pass data and some additional data and probably some signal to say whether it should be flushed or not. Is that right?
Yeah, kind of.
You
but
can embed all the data part into one data component, right? You can have your nesting of your data structures or structures itself. So the framework is looking as just data and some signals. I don't want to look into the data. It's not my problem. I'm only controlling the flow, right? And I don't want the pipeline to stall. I don't want to give the control to the programmer.
Okay, thank you.
I think.
This looks like very much similar to reactive streams.
What streams?
Reactive streams.
I'm not aware of that.
Anyways, so my question is, with this type of processing, how do you handle back pressure, where the data is flowing at a faster speed than you can actually process them in different stages?
I think like that should happen like very early on before you even put it on the stream. Once the stream gets triggered, like it just goes. I don't think this flow controller should get involved. Yeah, so it's always flows in one way in this stream. You cannot push back. It probably breaks our design to pass something back the chain. You can have a double pointer kind of thing. So here you have a single linked list. You just flow one way. But if you start doing backlinks, it will get little complicated. But maybe we can say, hey, I cannot process. Please stop.
Right. So there are some frameworks which actually notify upstream
Hmm.
that I cannot handle anymore.
Yeah.
And second question I have is, what happens when, let's say, division by 0 error happens? So how does your framework handle that?
So the whole pipeline breaks.
Okay. All right.
Yeah. I don't think we can really protect from that. So because we are giving the control of the function to the programmer itself, we are not writing it. So as a framework, if you are making something wrong in the flow control, like it's a framework's problem. If you can definitely screw yourself by writing a bad stage function, right? A filter, a mapper, or a reducer, whatever it is. But again, it's part of the testing. Okay.
Hello. Yeah.
Sorry.
Thanks for the great talk. Actually, first time I came to know about this concept of transducers. So how different is this from chaining, map, and filter, and all these different functions together?
Transducer is
Other languages like functional languages like Ruby.
Yeah,
for
it
example,
is
you chain, map, filter, and different
correct.
things together. So how is this transducers different from that?
Transducer is not very different. It's just behind the scenes. Okay, so transducer is the same thing which is borrowed from a functional programming. So where you are saying that what is the job of each stage and how it relates to the other stages. That's it. So it's not very different. So like if somebody is familiar with the Hadoop's MapReduce framework, their framework is a pipeline model, right? But there are few downsides because it's a stalling pipeline because all the local reducers will finish before you call the final reducer and the finalizer. It's a different way of flow control, but everybody is kind of doing the same thing. So because MapReduce also does a very good job of abstracting the notion of data and the signals, right? It is controlling the flow, but it's an abstract notion of data. So what is the difference between like Hadoop's MapReduce and what we are proposing here is Hadoop's MapReduce is very limited in terms of how many stages you can have, right? So you can just have like one map, reduce, and finalize, if I'm not wrong. We are saying like it should be much more extensible. I can add more stages later, right? So maybe you build a pipeline, so tomorrow you think, okay, I have to do something more in between. You can just add a stage in between. So it's much more flexible model.
Okay.
Thank you.
Thank you so much, Sunil.